Welcome. Let's discuss the multiple choice question for the geometry regions for June 2023. In question 1, we have that a square pyramid is intersected by a plane passing through the vertex and perpendicular to the base. So let's understand the situation. A square pyramid, it's a pyramid where the base, it's a rectangular figure. Now the vertex of this pyramid, it is the upper point. And in geometry, a plane, it is a flat surface. So here we're saying, let's consider a flat surface that is perpendicular to the base. Well, if we do that, the intersection is going to be 90 degrees. And now if we connect the intersection of the pyramid with the vertex, then notice that this flat surface that we are creating here, it has the shape of a triangle. And now when we take a look at the multiple choice questions, for which two-dimensional shape describes the cross section, which is the region in pink, well, it is option number 2, a triangle. Let's take a look at question 2. In question 2, we have a trapezoid ABCD, which is drawn in such a way that we have two parallel lines, AB parallel to DC. AB is on the right-hand side, and DC is also on the trapezoid in the right-hand side. Now there is an image, A prime, B prime, C prime, D prime, that occur when the trapezoid of ABC had a rotation of 110 degrees counterclockwise around the point of P. Well, let's understand the situation. So we started with a trapezoid on the right-hand side, which we call it ABCD, and then we perform a rotation of 110 degrees, and that gave us the trapezoid of A prime, B prime, C prime. And the rotation occurred around point P, which we have it here at the bottom. Now, what we want to know is which of the following statements are true. Since rotation was the action that was performed, let's think about some properties that occur with rotation. Well, first, a rotation, it is a Regent motion. Therefore, the image will be congruent to the pre-image. And in addition, any property that we had on the pre-image, the image will have the same property. So let's combine these two ideas. Because AB was parallel to DC on the image, A prime B prime will also be parallel to C prime D prime. And notice that that is option 3. Let's take a look at question 3. In question 3, we're interested on the volume of a right circular cone that has a height of 7.2 centimeters and a radius of 2.5 centimeters. So let's draw this cone. And now let's put down some information. The height was a 7.2 and the radius was a 2.5. Well, if volume is what we're interested, we have a formula for that. The volume of a cone, it is equivalent to 1/3 times the area of a circle, pi r squared, times the height of the cone. And notice that we have all the information, because when it comes to the radius, we have it as 2.5, and when it comes to the height, we have it as 7.2. So now let's plug that information. The volume is 1/3 times pi 2.5 squared, and all this we're going to multiply times the height, which is 7.2. Now when we place all this information in any calculator, we're going to get the value of 47.1, which is option 2. In question 4, we are working with the right triangle. And we are being given information that angle N, it is the right angle. So let's highlight that in here. And then in addition, we are being given two line segment SU, which we have it here as 13.6, and SN, which we have it here as 12.3. And what we would like to know is, what is the measurement of angle S? So let's identify that. That's the angle right here on the bottom left-hand side. Let me call this my reference angle. Anytime that we're looking for an angle in a right triangle, we want to use trigonometric functions. And to figure out which trigonometric function we're going to use, let's label our right triangle. When we take S as our reference angle, then the side that is opposite to that, it is UN, so that will be my opposite side. What is in front of 90 degrees? That is our hypotenuse. And whatever we have left, that's our adjacent. And now let's think about the acronym that we have to identify trigonometric function. The acronym of SOHCAHTOA. SOHCAHTOA. And now when we take a look at our right triangle, notice that we have information about adjacent and hypotenuse. And the function that has adjacent and hypotenuse, it is cosine. So now let's set this up. We are saying that if we take the cosine of our angle S, that is equivalent to adjacent over our hypotenuse. Well, now let's actually plug the information. Then we have that the cosine of S, it is equal to adjacent, which we have it as 12.3, over the hypotenuse, which we have it as 13.6. Well, to isolate angle S, we're going to multiply it by the inverse of cosine on the left and the inverse of cosine on the right. And this way, the cosines will cancel out, and now we just have angle S, which is what we're looking for. And that's equivalent to the inverse of cosine evaluated at 12.3 divided by 13.6. And when we place this in any graphing calculator, we're going to get that S is approximately 25 degrees. Let's take a look at the next question. In question 5, we're being given a circle whose name is O, where the diameter is the line segment AOB. And we have a chord of CV. And then in addition, we are being given a measurement of an angle. Angle B is 28 degrees. And what we would like to know is, what is the measurement of the arc of BC? Which we have it here in orange. Well, since AB was the diameter of the circle, then the arc from A all the way down to B, it is equivalent to 180 degrees. And now when we consider these two chords, AB and BC, then the arc of AC, it is equivalent to 2 times 28 degrees, because angle B is an inscribed angle. Which is equal to 56 degrees. And now we have all the information that is needed. Because notice that the arc of BC, it is equivalent to the green arc minus the blue arc. But the green arc was 180 degrees. And the blue arc, we just found it to be 56. So therefore BC, it's 124 degrees. which is option number 2. In question number 6, we are being given a parallelogram ABCD, which notice that is the exterior part of the figure given below. Well, if it's a parallelogram, then opposite sides must be parallel to each other. Therefore, AB, it's parallel to DC. And AD, it's parallel to BC. But what we're also given is that EF is perpendicular to DFC. Well, if EF is perpendicular to DFC, then their intersection is of 90 degrees. And we're also given that angle DAB, it's 111 degrees, which we have it here. And DBC, it's of 39 degrees, which we have it here. What we would like to know is, what is the measurement of angle DEF, which we have it here in our figure. So now let's try to see what information we can get from parallel lines. Well, how about we consider the line segment AB and DC, and we consider the transversal of DB. Well, when we do that, notice that this angle of 39 degrees, it is congruent to this angle that we have here on the bottom left-hand side. They are alternate interior angles. So we have a measurement of 39 degrees. And now notice that I can concentrate on this triangle that I'm going to highlight here in yellow. Because here we have 111 degrees and we have 39 degrees. Then we can identify what this angle is. So if I call this B, then I'm going to say that angle B, it is equivalent to 180 minus the interior angles, which is equivalent to 30 degrees. So let me place that in our figure. So now let me consider my parallel lines one more time, AB and DC, and the transversal of BD. Because notice that when I do that, this angle of 30 degrees, it is going to be congruent to this angle that we have inside as well. They are alternate interior angles. And now that I know that the angle is of 30 degrees, then I can concentrate on this triangle on the bottom. Where I know that this is 90 degrees, we have already established that this is 30 degrees. And now I can solve for the angle that we were looking for, DEF. Because now angle DEF, it is equivalent to 180 degrees minus the interior angles of this purple triangle, which is 30 degrees and 90 degrees, which is equal to 60 degrees. And notice that is option 3. In question 7, we are being given a triangle ACT. And then in addition, we are being given that the line segment of ES, which we have it here, it is parallel to the line segment of AT, which is the base of our triangle. So let me clean this up. So ES was parallel to AT. And what we would like to know is which of the following ratios are true. Well, here we have in a specific scenario. Anytime that we have a parallel line to the base of our triangle, then the sides of our triangle, which is AC and CT, are cut in proportion. In other words, if we get the first section, EC, and we divide it by the second section of AE, that is going to be equal to the upper section in the right divided by the lower section in the right. And notice that is option number 3. So this question was more about identifying anytime that we have a parallel line to the base of a triangle, then the sides of the triangle are always cut in proportion. The upper divided by the lower on the left, it is equal to the upper divided by the lower in the right. In question number 8, we are being given two triangles in a plane. Triangle ABC, which we have it here on the left, and triangle DEF, which we have it here on the right. And what we would like to know is which maps of transformations get triangle ABC into triangle DEF. Well, let's think of a strategy. Well, we are being given information that we have congruent triangles. So let's identify corresponding sides. The first letter in ABC is going to be congruent to the first letter in DEF. So angle A is congruent to angle D. The second letter, which is B, is going to be congruent to the second letter, which is E. So let's put those down in blue. And angle C is going to be congruent to angle F. Now let's think about orientation. Let me choose the middle angles in ABC and DEF, which are the blue ones. But if I'm looking at the perspective of B, notice that A, it is above angle B, and angle D, it is to the left-hand side of angle E. And when we take a look at the orange point, which is angle C, we started facing to the left-hand side of the blue, and then we end up facing to the bottom side of the blue. So we can change this orientation by considering a rotation of 90 degrees. So let's visualize this. This arrow that was facing up, if we rotate it 90 degrees, then now is going to be facing to the left, which is exactly the scenario that we have here. Instead of facing up, now we're facing to the left. And this orange arrow, which we start facing to the left, after a rotation of 90 degrees, then we start facing downwards, which is the scenario that we have here with the orange. We were facing to the left, and then we end up facing downwards. But let's remember our rule for rotation of 90 degrees. If we are being given any coordinate point x, y, after the rotation, it becomes negative y, x. So the original point that we were given of A, it had a location at negative 2, 6. So after our rotation, which is A prime, is going to end up at negative 6, negative 2. Let's place that in our diagram. So here we have A prime. So now this point of C, it had a location at negative 5, 2. After the rotation, let's call it C prime, we're going to have a location at negative 2, negative 5. So this is where we're going to find C prime. And this blue point of B, it had a location at negative 2, 2. Then after the rotation, its new location, it's at negative 2, negative 2. Which we have it here. So this is the triangle that we obtain after a rotation of 90 degrees. So now notice that it's starting to look a lot like the image that we wanted to map it to. The green point is on the left, the blue is on the upper right, the orange is on the bottom right. Now, if we get this red triangle and we move it 8 units to the right, notice that every single point will be mapping. A prime, when we move it 8 units to the right, is going to map to point D. B prime, if we move it 8 units to the right, is going to map at E. And C prime, 8 units to the right, is going to map to F. So we have identified our transformation. First, it was a rotation of 90 degrees counterclockwise. And then it was a translation of 8 units to the right. And notice that that is option 1. Let's take a look at the next question. In question 9, we are being given the equation of a circle as x squared plus y squared plus 6x minus 2y plus 1 equals 0. And what we would like to do is find the coordinates of the center and the length of the radius. But notice, though this equation that is given to us is not written in standard form. The standard form of an equation of a circle is x minus h squared plus y minus k squared, and that is equal to the radius squared, where the center is at h comma k, and the radius, it is equals to r. So the objective of this question is, let's consider the equation that we are given and rewrite it in standard form. Because once we have it in standard form, then we can identify what we are looking for. So let's start by writing out the equation that we are given. The first thing that we're going to do is, let's leave all the variables on one side and all the constants on the other. So let's subtract 1 to both sides, and that way, on the left, there's only variables. Now that we only have variables on the left, let me organize my equation. Let me just write the value of x's first. And then I'm going to write down the variables of y. What I have done so far, I have just organized my equation. I'm writing all the x's first, and then I'm writing all my y's. Now what we are going to do, we are going to complete the square on the variable of x and the variable of y. So let's start with the variable of x. Let me get the value that is in front of x, which is equivalent to 6. And I'm going to complete the square. I'm going to divide it by 2. That is going to be equals to 3. And then this value, I'm going to square it. That is going to be equivalent to 9. Now this value of 9 that we have here, I'm going to add it to the equation right after the x's. And I'm going to do the same with the y's. Let me get the value that is in front of y, which is -2. And I'm going to do the same. Let me divide it by 2, which is -1. And this value, I'm going to square it, which is equals to 1. And now this value that we obtain, I'm going to add it right after the y's. And now to balance the equation, because I added 9 on the left, I should do it on the right. And because I added 1 on the left, I should do it on the right as well. And now notice that when I'm concentrated on the x's, I can fact this out. Two values that if I multiply gives me 9, and if I add them up, gives me 6. Well, that will be 3 and 3. So this expression of x squared plus 6x plus 9, I can write it out as x plus 3 raised to the second. And when I concentrate on the y's, now I can factor that out. Think of two numbers that if you multiply gives you 1, and if you add them up gives you -2. Well, that is -1 and -1. So this expression can be factored out as y minus 1 all to the second. And when I combine the right-hand side, well, that is equals to 9. Now, before we move forward, if you're not too good about factoring, here's a shortcut. That value that we square it for the x's is the value that goes inside the parentheses, and that value that we square for the y's is what goes inside the parentheses for y. Now, note that the result that we obtain in here, it looks a lot like the standard form. But instead of calling it 9, I need to represent it as r squared. So instead of 9, I'm going to represent it as 3 squared. Now we are good. Here we have our standard equation of our circle. So now, when it comes to the center, it is h and k, which in this case, it is -3 and +1. We always switch the sign. And when it comes to the radius, it is equivalent to 3. And notice that this is option 4. Now, in question 10, we are being given a parallelogram, BETH, which is the outside of this figure. And we also know that there are two diagonals, BT, which we have it here, and HE, which we have it here. Now, what we would like to know is which additional statement will be sufficient to prove that BETH it's a rectangle. Well, let's think about what needs to happen for us to have a rectangle. Well, if we want to claim that this figure is a rectangle, then two things needs to be shown. Opposite sides are congruent to each other, and then in addition, interior angles are 90 degrees. So now let's see which of the following statements gives us these two requirements. Well, to start with, don't forget that BETH is a parallelogram, and within a parallelogram, opposite sides are congruent to each other. And at least in here, we have fulfilled the first condition. And also, in addition, opposite sides are parallel to each other. Now we want to think about how can we guarantee that the interior angles are 90 degrees? Let's go one case at a time. So let's consider option number 1. BT is perpendicular to HE. If BT is perpendicular to HE, all that we are saying is that the intersection are of 90 degrees. But that doesn't show that the interior angles are of 90 degrees. So perhaps option number 1, it is not the correct option. Now let's consider option number 2. BE is parallel to HT. Well, BE is right here and HT is right here. That was already a given. That's a property of a parallelogram. So option number 2 will not be an okay option. So now let's concentrate on option number 3. BT is congruent to HE. So BT, it's right here, and HE, it's right here. So we are saying that diagonals are congruent to each other. How about if I consider one diagonal at a time? Let me just consider diagonal BT. And when I do that, I can consider this triangle in pink, BET. And when I consider the other diagonal, EH, I can consider this triangle, HET. Now, is there anything that we can say about these triangles? Well, to start with, BE is congruent to HT. That was a property of a parallelogram. Well, they both share the line section of ET, so it must be congruent to itself. And right now we're considering that BT is congruent to HE. So we're saying that this section is congruent to this section. So now notice that right now we have two congruent triangles by side, side, side. And now, how about if we consider the corresponding angle of E and T? They are both in front of the congruent diagonals. But don't forget that we're working with a parallelogram. And within a parallelogram, adjacent sides are supplementary. And now let's mix this idea together. If I add E and T, that must be equivalent to 180 degrees. And in addition, I know that they are congruent to each other, then there is only one number that will satisfy these two conditions. That is 90 degrees. So we are done. We have shown that we actually have 90 degrees in angle T and 90 degrees in angle E. Therefore, option number 3 will be the correct option. In question 11, we have that a gardener, he wants to buy enough mulch to cover a rectangular garden where the dimensions of this garden is 3 feet by 10 feet. So let's visualize that. Here's our rectangular garden, and our dimensions are 3 feet by 10 feet. Now we're also given that one bag that contains 2 cubic feet of mulch, it costs approximately $3.66. So let's write that on the side. Now we would like to know is how much will the minimum number of bags will cost to cover the garden with mulch that is 3 inches in depth. So let's put this information in our diagram. On the left we have our garden. So now let's say that when it comes to depth, it is of 3 inches. But before we move any further, here's a conflict. Because notice that the dimensions of the garden are in feet and the depth is in inches. Well, let's convert these inches into feet. And when we do that conversion, 3 inches is equivalent to 1/4 of a feet. So let's write down our strategy. First, we're going to find the volume of the garden. Because once we have the volume of the garden, then we can figure out how many bags are needed. One bag will cover 3 feet cubed. And once we have this volume, we can figure out how many bags are needed. And once we know how many bags are needed, then we're going to multiply the number of bags times the cost. Let's perform that calculation. When it comes to volume, we can treat this as a regular prism. And to find the volume of a regular prism, it is the area of the base times the height. Well, the base of our figure, it is 3 feet times 10 feet. And when it comes to our height, well, that is the depthness of our garden, which is 1/4 of a feet. So 3 times 10, that's 30, times 0.25, well, that's equivalent to 7.5 feet cubes. But now that we know what's the volume, now we can think about how many bags are needed to cover this volume. Well, each bag, it covers 3 feet. Well, if we do one bag, that is 3 feet, we need more. Well, if we do 2 bags, that's going to cover 6 feet. But notice that we still need more than 2 bags to cover 7.5. Well, with 3 bags, we will cover a total of 9 feet. And that will be sufficient to cover the 7.5 feet cube that we need for this garden. And now that we know how many bags are needed, well, we know the cost that each bag is of 3.66. Then we're going to get 3 times 3.66, and that is going to give us the total cost to cover this garden, which is 14.64, which notice that is option number 3. In question 12, we have the following. We are working with 2 similar triangles, DOG on the left and CAT in the right. And then in addition, we are being given 2 right angles, G and T, which we have it here. What we would like to think about is, if I consider the expression of sine of D, which of the followings are going to be equivalent to? Well, let's start with that expression. Well, remember that the sine of any angle that is equivalent to opposite over hypotenuse. So let's start by labeling our triangle. Angle D, we have it here, is the upper angle in the triangle in the left. Well, the side that is opposite will be my opposite side, GO. What's in front of 90 degrees, that will be my hypotenuse. And what is left, it's our adjacent. So if we put all this together, then we can say that the sine of angle D, it is equivalent to the opposite, which we have it as GO, divided by the hypotenuse, which we have it as DO. So now we have our objective. So now let's think about which of the following options is equivalent to the expression of GO divided by DO. So now let's use the information that we're working with similar triangles. Because if we have similar triangles, then we have proportional sides. The first two letters in our triangle in the left is DO. Well, that's going to be proportional to CA. Let's put that in our figure. DO, which is in blue, it is proportional to CA. Let's also put it in blue. And now when I take out the second and third letter, OG, well, that is going to be proportional to AT. GD is going to be proportional to the third and the first letter as well, TC. So therefore, we can rewrite this expression. Now, GO was the line segment that we highlighted here in pink. And DO was the expression that we highlighted here in blue. Because of similar triangles, then that should be proportional to the pink divided by the blue in the triangle in the right. And that will be TA divided by AC. And now we have a better strategy. How about we think about which of the following four options is equivalent to the expression of TA divided by AC, because we know that they're equivalent because of similar triangles. One thing that I noticed is that the majority of the options have angle A. So let me start with that. Let me consider angle of A and let me label the triangle in the right. TC will be my opposite. AC will be my hypotenuse. And what is left is our adjacent. When we consider A as our reference angle, then notice that TA, it is our adjacent, and AC is our hypotenuse. So now we're going to think about which trigonometric function is equivalent to adjacent over hypotenuse. Adjacent divided by hypotenuse, that is cosine. So now we can say that this expression is equivalent to the cosine of our reference angle. And right now, we're using angle A. So we are done. That is option number 1. Let's just summarize what we have said here. We started with the sine of D, and that was equivalent to GO divided by DO. But because we're working with similar triangles, then that's equivalent to TA divided by AC. But TA divided by AC, it is the adjacent divided by the hypotenuse in the triangle in the right when we are working with angle A. So now we can say that sine of D, which is where we started, is equivalent to cosine of A, which is option number 1. In question 13, we are being given a set of axes below where triangle DEF, which is this little triangle that we have here at the bottom, is the image of a big triangle ABC, which we have it here in the left, after a dilation of a factor of 1/3. And what we would like to figure out is, what is the center of dilation? Well, let's start matching whose point got dilated to who. The first letter, which is angle D, let's put this in red, got dilated to angle A, which we have it here. The second letter, which is angle E, which we have it here, it got dilated to the second letter, which is B. And the third letter, angle F, got dilated to angle C. So F got dilated into C. But because we are being given a set of axes, then let's draw the line of dilation, connecting every image with and pre-images. So let's connect A and D. There are images and pre-images. Let's connect B and E. There are images and pre-images. And let's connect C and F. There are images and pre-images. And notice that all lines are intersecting at this location, at the location of 2, -3. Well, that is where we're going to find our center of dilation, which is option number 2. In question 14, we are being given an isosceles triangle AHE. which is the outside of the figure below, with a vertex angle of h. So let's put that down. This is our vertex angle. And then in addition, CB is perpendicular to AE. So if CB is perpendicular to AE, their intersection is 90 degrees. And then also, FD is perpendicular to AE. So if FD is perpendicular to AE, their intersection is also 90 degrees. What we would like to know is which of the following statements are true. But when I'm looking at all the statements that we are given here, they're all proportions to the sides in this figure. But one way to obtain proportions of sides is by identifying similar figures. So that's our strategy. Let's try to identify similar figures. Well, let's start with this piece of information. We are working with an isosceles triangle. Well, because we have an isosceles triangle, then the following are true. We have two congruent sides. The ones that are intersecting are vertex angle. So that will be AH and HE. And then in addition, the opposite angles are also congruent. So we can say that angle A, it is congruent to angle E. And at this point, I can kind of stop because I can concentrate on this triangle in the left and also this triangle in the right. Because I can claim that those two triangles are similar by angle-angle similarity theorem. We have two angles in the triangle in the left, which are congruent to two angles that are on the triangle in the right. So let me draw them individually. So now let's identify proportional sides. Those sides which are in front of the pink angle and FD, they are going to be proportional to the sides that are opposite of the right angle, which in this case is AC and FE. And they are also proportional to the sides that are left, AB divided by DE. So we know that this is a true statement. All three proportions are equal to each other because we have similar triangles. And notice that when I'm just concentrated on the second and the third, it matches up with option number 2, which is the correct option. In question 15, we have a rectangle ABCD. When we are being given two coordinate points, the coordinate point for A and the coordinate point for B. And what we would like to know is, what is the slope of the line segment BC? So let's start by plotting those points. So let me approximate their locations. So let's say that this is our x and our y axis. A is -1, -3. That should be somewhere around here. B is 6, 5. So that should be somewhere around here. So now let me connect those dots. And because we're working with the rectangle ABCD, let me just create some rectangle. Well, let's follow the lettering. The name is ABCD. So if we go from A to B, then the next letter in this order will be C. And then the next letter will be D. So let's identify the objective, which is the slope of BC. So we would like to know the slope of this line. But here's a problem. If we want to find the slope of a line, we need 2 points. And at least we know the coordinate point of one of them, B, but we have no information about C. So we cannot use the typical slope formula to find the slope of BC, but remember that this is a rectangle. And if it's a rectangle, then we know that every interior angle, it's 90 degrees. Then notice that we can say that AB is perpendicular to BC. Their intersection, it's of 90 degrees. But if two lines are said to be perpendicular, then their slopes are negative reciprocal. So that's our strategy. We are going to find the slope of the line segment of AB, and then we're going to take the negative reciprocal, and that is how we're going to find the slope of BC. So let's do that. So let's subtract the y's, 5 minus negative 3. And then let's divide by the difference of x's, 6 minus negative 1. So we are going to get 8 divided by 7. Well, the negative reciprocal of 8 divided by 7, it is 7 divided by 8, changing the sign, negative. And notice that that is option number 1. In question 16, we are being given a right triangle ABC with angle measurements where A is 90, B is 18, and a line segment where AC is equivalent to 8. So let's start by drawing this triangle. So angle A is 90. Let's draw that in here. Angle B is 18 degrees. So let's place that in here. In line segment, AC is of 8. What we would like to know is, what is the length of the line segment BC? Which we have it here. So let's understand the situation. We are working with the right triangle, and we would like to find one of the sides of this right triangle. When we have this situation, we want to use trigonometric functions. So to use trigonometric functions, let's label our sides. What's in front of 90 degrees, that's our hypotenuse. Let's use angle B as my reference angle. So what's in front of angle B will be my opposite. And what is left? It's our adjacent. So within this right triangle, we have information about our opposite, and we will like information about the hypotenuse. So now let's think about which trigonometric function will help us with that. Well, let's remember our acronym, SOHCAHTOA. And if opposite is what we have and hypotenuse is what we want, then notice that we can use the sine function. Sine is opposite over hypotenuse. So we are going to have the sine of our reference angle, which notice that we use B to label our triangle. So that is 18. That is equal to the opposite, which we have it as 8, over the hypotenuse, which is what we want, BC. So now let's try to solve for BC. Well, the left-hand side, I can divide it by 1. Now I can cross multiply. The sine of 18 is going to get multiplied times BC. And that is going to be equal to 1 times 8. Well, if we want to solve for BC, let's divide by the sine of 18 on both sides. I can see that I'm running out of space, so let me write that down here on the left. So now we're going to see that BC is equivalent to 1 times 8, which is 8, divided by the sine of 18. And when we put this in our graphing calculator, it's going to give us an approximation of 25.9. Which notice that that is option 4. In question 17, we're given that the measure of one of the base angles in an isosceles triangle is 42 degrees, and what we would like to know is the measure of the exterior angle at the vertex of our triangle. So let's visualize this. Here we have our isosceles triangle. And if it's an isosceles triangle, there are two congruent sides, and those angles opposite to it are congruent as well. Well, these angles that are congruent are what we refer as base angles. And this angle that is not congruent is what we refer as the vertex angle. So the exterior angle at the vertex of this triangle, it occurs when we extend the line that creates that vertex angle and we consider the angle that we are creating. And this is what we're looking for. What is the measurement of this angle displayed in purple? Well, let's put some information down. We are being given that the base angles are of a measurement of 42 degrees. So we have 42 degrees in here and 42 degrees in here. And with this information, we can find the measurement of the vertex angle. The summation, it is equal to 180 degrees. So we can have 180 minus 42 minus 42. That is going to give us 96 degrees. And now notice the relationship between the exterior angle and the vertex angle that we have here. When we add them up, we are creating a straight line. And a straight line, it's always equivalent to 180 degrees. So now let me move this. Then we can create an equation. We can say that 96 plus the exterior angle, let me just call it EA, well, that is equal to 180 degrees. Well, if we subtract 96 on both sides, then we're going to get that the exterior angle is equivalent to 84 degrees, which is option number 2. In question 18, we are being given two parallel lines, AFKB, which is this horizontal line on top, and CHLM, which is this horizontal line in the bottom. And we're also given that the line segment FH is congruent to the line segment of LH, where FH is this section in the left and LH is this section in the bottom. And also, FL is congruent to KL, where FL, it is this section in the left, and KL, it is the section in the right. And in addition, the line segment LF, it bisects the angle of HFK. So when we consider this angle of HFK, if LF bisects it, which is the section in here, then we can say that this angle in the left, it is congruent to this angle in the right. And now that we have all this information in our diagram, we want to see which of the following statements are true. But one thing that I notice is that this triangle that we have here in the left, it's an isosceles triangle. We have two congruent sides. So therefore, the angle in front of the reds are going to be congruent. So let me use the same notation. So this angle of HLF, it will be congruent to angle HFL. And also, I notice that I have another isosceles triangle in here. I have two congruent sides. So those opposite angles of the congruent sides are going to be congruent. So there's two angles that we have in here. So angle F will be congruent to angle K. So now I know that all those four angles are congruent to each other. So now let's try to see how we can use that we have two parallel lines. So how about if I use this transversal, the transversal of KL? Well, if that is the case, then this angle of K, it will be congruent to this angle of L. There are alternate interior angles. So I can use the same notation. So now notice the following scenario. Here we have this straight line connecting the points of DFL, and also we have a straight line connecting the points of HLM. And in this scenario, we know that we have two congruent angles in here. And let's draw the other scenario. When we consider this horizontal straight line, here we have two congruent angles, the one on the left in purple and the one on the right in purple. Well, notice that we can say that the angle of DFK is actually congruent to the angle of KLF when we consider a straight line. That is 180 degrees. And in both scenarios, we have that two congruent purple angles plus this angle that we have in red, it is equal to 180 degrees. This is this scenario that we have here. And we have the same scenario in here. So we can claim that those two angles are congruent to each other. And notice that that is option number 4. Angle DFK being congruent to angle KLF. In question 19, we have a line whose equation is 6x plus 3y equals to 3. This equation is dilated by a scale factor of 2. So let me write that down on the side. Our scale factor is going to be equals to 2. And then in addition, the center of dilation, it is at the point 0, 0. What we would like to know is, what is the equation of the image after this dilation? But before we even think about dilation, let's get the equation that we are given, and let's write this down in standard form. Let's solve for y. So let's start by subtracting 6x to both sides. And then let's divide it by 3. And now we're going to get negative 6 divided by 3, that's negative 2. And 3 divided by 3, that's 1. So this is the equation that we are going to consider. So now let's visualize this situation. The equation that we were given, it has a y-intercept at y equals 1. And we also have a slope of negative 2. So let's graph this line. Y-intercept at 1. The slope is negative 2. So from the y-intercept, I'm going to move 2 units down and 1 to the right. Let me just do that one more time. 2 more units down and 1 to the right. And when we connect these points, here we're going to have the equation that we were given at the beginning. Now let's place our center of dilation, which is at the origin, 0, 0. Now, if we have a scale factor of 2, what we are saying is, if I look at the distance from the center of dilation to any point, I need to double that distance. The distance is of 1. Let me double it. And now in here, I'm going to get the image after the dilation. And the same goes with any other point. Let me find the distance from the center of dilation to this point that we have here. But the movement is 1 unit down and 1 unit to the right. So let me repeat that movement one more time. Let me move another unit down and another one to the right. And I'm going to get this other specific point. Now let's connect those points. So this line that we have here in green, it is the line that we were given after a dilation of a scale factor of 2. Well, let's identify two key properties of this new line, the y-intercept and the slope. Well, notice that the y-intercept is at the value of 0, 2. And when it comes to the slope, we will always have the same slope as the line that we were given, -2. And now when we combine these two ideas, we're going to have y equals -2 of x plus 2. This is going to be the equation after our dilation. And notice that it matches option 2. So some ideas to consider is that the equation that we are given will always be parallel after the dilation. So we will share the same slope. And then in addition, when we take a look at the original equation, the y-intercept, if we multiply by the scale factor, it will always give us the y-intercept of the line after the dilation. So that would have been a faster way to get our answer as well. In question 20, we want to figure out which of the following figures will not carry into itself after a rotation of 120 degrees about its center. And the first thing that I notice is that when I take a look at all the options that we are given, they are all regular figures. And regular figures have rotational symmetry. It is 360 divided by the number of sides that we have in the figure. Let's start by looking at equilateral triangles. Let's draw that. The rotational symmetry of this figure, which I'm going to abbreviate by RS, it will be 360 divided by the number of sides, which in this case, we have 3. So that is equivalent to 120 degrees. So what we are saying is, when I look at the center of the figure, if I rotate it 120 degrees, the triangle will overlap with itself, which is the opposite of what we're looking for. We want for the figure that will not carry into itself in a value of 120 degrees. Well, an equilateral triangle does it. So therefore, option number 1 is not what we're looking for. Let's look at option number 2. A regular hexagon. A hexagon will have 6 sides. So let's draw that. Now let's find its rotational symmetry. That will be 360 divided by 6, which is equivalent to 60 degrees. Now, maybe at this point, you might be saying, well, obviously 60 is not equivalent to 120. So therefore, the correct option is number 2. Well, that is not correct, because even though we got a value of 60 degrees, any multiple of 60 degrees will also carry the figure into itself. And notice that 120, it's equivalent to 2 times 60. 60, when you have a multiple of 2, it's equivalent to what we are looking for. Therefore, a regular hexagon will carry the figure into itself after a rotation of 120 degrees. Option number 2 is not the correct option. We're looking for the knots. Let's look at option number 3. A regular octagon. A octagon has 8 sides. So let's visualize that. Well, its rotational symmetry will be 360 divided by 8, which is equivalent to 45 degrees. So what we are saying is, every time we rotate 45 degrees, we are going to overlap the figure into itself. Well, notice that 120, it's not a multiple of 45 degrees. The correct option is number 3. In question 21, we have a triangle ADF, which is the outside in the figure given below. And then in addition, we have two parallel lines, BC and DF, where BC is right here and DF is right here. And what we would like to know is, which of the following statements are true? Well, anytime that we are being given information about parallel lines, we might want to think about, is there any congruent angles? So let's start by considering these two parallel lines, CB and FD, and the transversal of AF. So let's draw this more clearly on the right-hand side. And let's not forget that the green lines are parallel to each other, where this intersection is point F in our figure, this intersection is point C in our figure, B it's right here, and D it's right here. Well, let me start by identifying corresponding sides, which in this case, this orange angle of CFD, it is congruent to this orange angle CVA, where A is right here in our figure. Well, let's identify that in the triangle given to us. That will be this angle right here, and that will be this angle right here. Well, we're actually done, because notice that that is option 4. ACB, which we have it here, is congruent to AFD, which we have it in here as well. And we have just shown that those two angles are congruent to each other because they're corresponding angles. So option number 4 is the correct one. In question 22, we have a triangle ABC. So let's start by drawing that, where M is the midpoint of AB. So let's draw that in here. That's about here. And then in addition, N is the midpoint of AC. So that's about here. And within this scenario, we are being given two line segments. The length from M to N, which is this section, is equivalent to x plus 13. And the length from B to C, it's equivalent to 5x minus 1. So if we connect the points B to C, that is equivalent to 5x minus 1. What we would like to know is, what is the exact length of M and N, which is one of the expressions that we were given. Well, one thing to notice is that the line segment MN, it is the connection of two midpoints in a triangle. And the median, it has some properties. When it comes to the length, the base of a triangle will always be twice as large as the median of the triangle. And this just happens to be the lengths that we are being given, because the base of our triangle is the line segment of 5x minus 1, and the median, we have an expression for that, x plus 13. So we can set up an equation. The base of our triangle, which is 5x minus 1, will always be equal to 2 times the length of the median, which we have it as x plus 13. And now with this equation, we can solve for x. Well, let's start by distributing the 2. So we will have 2x plus 26. And now to solve for x, let's move this 2x to the other side. So we'll have 3x minus 1 equal to 26. So now let's add a 1, both sides. We'll have 3x is equivalent to 27. And now let's divide it by 3. So now we can say that x is equivalent to 9. But let's not choose option number 2, which is 9, because this question did not ask for x. This question asked for the line segment of MN. So let's eliminate 9. But the good thing is that we do have an expression for MN. We set that to be x plus 13. But now we know what x is. X is 9. So we'll have 9 plus 13, which is equivalent to 22. So the real correct answer It is option 4. In question 23, we have a diagram of an isosceles trapezoid star, which is the outside of the figure given below. And we're also being given diagonal AS and diagonal RT, where they intersect at point O, where AS, we have it here, and RT, we have it here. And notice that they're intersecting at some point called O. And lastly, we're given that the line segment ST and RA are parallel. So let's actually put that in the diagram. ST is the upper line segment, and RA is the bottom line segment. And lastly, SR and TA, they're just line segments. They are non-parallel. And what we would like to know is which of the following segments are not always similar. So essentially, we are looking for similar triangles. But let's remind ourselves, what are some ways to show similar triangles? Well, we have the angle-angle similarity theorem. We have the side-angle-side similarity theorem. And we have the side-side-side similarity theorem. So if any of these 4 options satisfy any of these 3 theorems, then we know they are similar, so we will not consider them as a correct answer. Well, let's not forget that we're working with an isosceles trapezoid of star. And there are 2 properties that isosceles trapezoid have. First, the legs of the trapezoids are congruent. Those sides which are not parallel to each other, which in this case, that SR and TA. And then in addition, those angles opposite to the legs are also congruent to each other, which in this case, that will be the whole angle of A and also the whole angle of R. So let's consider that when we look at the following scenarios. Let's clean this up. Let's look at scenario number 1. Triangle STO, it is this upper triangle. In triangle ARO is this bottom triangle. So let's draw those triangles. Well, one thing to notice is that here we have vertical angles. So we got 2 angles that are going to be congruent within the figure. Well, when I consider this transversal of RT, I'm going to have 2 alternate interior angles with the parallel line of ST and RA. So we're going to claim that this bottom angle is congruent to this upper angle. And at this point, we can stop. Because in scenario number 1, we have 2 triangles with 2 congruent angles. So we can use angle-angle to show that they're similar. But remember that we're looking for the knots. So option number 1 is not the correct option. Let's look at option number 2. Triangle SOR is similar to triangle TOA. So let's draw those triangles. But just as we did with the previous example, here I have 2 vertical angles. Let me place those in our triangles. So how will we consider the diagonal of SA? But this diagonal of these 2 parallel lines will produce 2 congruent angles. Angle S and angle A. They are alternate interior angles. And at this point, we can stop. Because notice that again, we're satisfying the angle-angle similarity theorem. So option number 2 is not what we're looking for. Let's look at option number 3. Triangle SRA and triangle ATFs. So let's draw those triangles. So I can make the same observation as before, where this angle of SRA is congruent to the angle of TAS. They're alternate interior angles. And then in addition, we know that SR is congruent to TA, but that's all the information that we can gather about these 2 triangles. And notice that we're not satisfying either angle-angle similarity theorem, side angle side, similarity theorem, or side side side, similarity theorem. Therefore, in option number 3, those two triangles, we cannot show that they are similar. In question 24, we have a line segment AB where the coordinate point for A is 0, 4, and the coordinate point for B is -4, 6. What we would like to know is which equation of a line represents a perpendicular bisector of AB. Well, let's think about what we need to show. A perpendicular bisector, it must have two properties. First, it must be perpendicular. And second, it must bisect. It must pass through the middle. So let's start by visualizing this line segment of AB. So point A at 0, 4, it's somewhere around here. And point B at -4, 6, it's somewhere around here. So this is the line segment that we are given. Now what we're looking for, which is a perpendicular bisector, it must pass through the middle. And then in addition, it must be perpendicular. So let's start by identifying the intersection point. Well, if it must pass through the middle, then we can say that that is the midpoint between A and B. So let's use the midpoint formula to find that location. Well, remember the midpoint, it is when you add both values of x's and you divide it by 2, and when you add both values of y's and you divide it by 2. So in this case, the value of x's is -4 and 0. Let's divide it by 2, and the y's are 6 and 4. So we have a location. -4 divided by 2, that's -2. And 6 plus 4, that is 10, divided by 2, that is 5. Well, let's put this down. The midpoint, it's at -2, 5. Now, if we wish to find the slope of the perpendicular line, how about if we find the slope of the line segment AB, and then we use the negative reciprocal? Two lines are said to be perpendicular if they share a negative reciprocal slope. So now let's find the slope of AB. So to find the slope, let's subtract the value of the y's, 4 minus 6. And let's divide that by the subtraction of the x's, 0 minus -4. And on the numerator, 4 minus 6, that's -2. And 0 plus 4, that is +4. And we can simplify this as -1/2. So now let's put all this together. The line of the perpendicular bisector, it must pass through the point of -2.5. Notice that that is a point in the red line. And also, it must have a slope of the negative reciprocal of what we found. So if AB has a slope of -1/2, then the negative reciprocal is +2/1. Now let's define the equation of the perpendicular bisector using the point slope. Y minus y1 equals m x minus x1, where x1 and y1 are points in our line, and m, it is the slope of our line. And now let's simplify this. When we distribute the 2, it becomes 2x, minus and a minus, that is a plus. And when we distribute the 2, that becomes a 4. And now if we add 5 to both sides, we're going to get the equation of 2x plus 9, which is option number 4. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.